Welcome to Daily Papers, the podcast where we break down the latest research into bite-sized, easy-to-digest pieces.
Today, we're talking about AI assistants. You know, the chatbots you use to write code or draft emails. Have you ever been in a really long conversation with one and you feel like it's starting to slow down or maybe forget things you told it half an hour ago?
All the time, you end up repeating yourself and it gets frustrating. Well, a fascinating new paper argues that we've been thinking about AI memory completely wrong, and the solution might come from computer science ideas from the 1960s.
The paper is called The Missing Memory Hierarchy, Demand Paging for LLM Context Windows by Tony Mason, and it starts with a really bold claim. The context window of a large language model is not memory, it's a cache.
Okay, we need to break that down. First, what's a context window?
Think of it as the AI's short-term memory. It's all the information the model can see at any given moment. This includes your initial instructions, the entire conversation history, and any documents or code you've given it. Everything has to be crammed into this one space.
And the problem is that we keep cramming more and more in. Every time you send a message, the entire history gets sent back to the model. The paper measured this across hundreds of real-world sessions and found that almost 22% of what we're stuffing into that context window is basically junk.
Exactly. It's structural waste. Things like definitions for tools the AI never even uses, or the full text of a file it read on turn 1 of a 100-turn conversation. It's like trying to cook in a tiny kitchen and never putting any ingredients or dirty dishes away. Eventually, you run out of counter space and can't get anything done.
So what's this big idea from the 1960s that's supposed to fix our messy AI kitchen?
It's a concept called virtual memory and demand paging. Back in the early days of computing, memory was tiny and expensive, just like context windows are today. Programmers had to manually shuffle bits of their program in and out of memory. It was a nightmare.
Sounds tedious.
It was, so computer scientists invented a system that did it automatically. Think of the computer's fast memory, its RAM, as a small desk. You can only keep a few books on it. The computer's hard drive is a giant library next to the desk. Virtual memory is a clever librarian who watches what you're doing.
And what does this librarian do?
When your desk gets too cluttered, the librarian takes a book you haven't touched in a while and puts it back in the library, leaving a little bookmark on your desk that says, "The history of Rome is in the library." This is called eviction.
Okay, so your desk is clean again, but what happens when you suddenly need that book back?
You reach for the bookmark, and the librarian says, you need that book, and quickly fetches it from the library and puts it back on your desk. In computer terms, that moment of needing something that's been moved is called a page fault.
So the paper is saying we need a librarian for our AI's context window.
Precisely. The author built a system called Piche that acts as this librarian. It sits between the user and the AI. It sees that huge file the AI read an hour ago and hasn't looked at since, and it evicts it. It takes the file out of the context window and replaces it with a tiny little message, a bookmark that says, "Paged out, file.py. Reread if you need it."
And does the AI know how to use that bookmark?
That's the magical part. It does. When the AI needs that file again, its next action is to try and reread it. Piche sees this request, recognizes it as a page fault, and seamlessly provides the file's contents right back to the model. The AI gets what it needs, and the user's context window stays lean and efficient.
That is incredibly clever. Does it actually work in practice?
The results are pretty staggering. In one live session, the system reduced the amount of context being used by up to 93%, and the number of times it got it wrong, the number of page faults, was incredibly low. In a simulation of over 1.4 million evictions, the fault rate was just 0.0254%.
Wow, so the librarian is very good at predicting which books you're not going to need anytime soon.
Exactly, and this leads to another really mind-bending idea in the paper, which they call the inverted cost model.
Inverted cost model. Go on.
With our librarian analogy, keeping a book on your desk is free, but the fault, making the librarian run to the library to get a book, is expensive because it takes time. In traditional computers, the goal is to minimize faults.
Right, that makes sense.
But with LLMs, the economics are flipped upside down. Keeping stuff in the context window is incredibly expensive because you pay for every single token to be reprocessed every single time you have a conversation turn. But faulting, just rereading a file once when you actually need it, is super cheap in comparison.
So the best strategy isn't to avoid faults, it's to be really aggressive about evicting things from the context window. You should be throwing books back to the librarian constantly.
Exactly. You want to keep your desk as empty as possible. This is totally backwards from how computer memory has been managed for the last 50 years, but it's the right model for AI.
So this system, Piche, is essentially a memory manager for language models, creating a whole hierarchy of memory, from the super fast, expensive context window down to a slower, cheaper storage space.
Yes, and there's one more cool trick. Unlike a normal computer program, you can actually talk to an LLM, so Piche gives the model special tools to let it help manage its own memory. The AI can literally say, hey, I'm done with this file now, you can evict it. Or, I'm about to start a big planning phase, I'm going to need these 5 files, can you please make sure they're available?
The processor is helping to manage its own cache. That's not something you see in traditional computing.
It's a whole new design space. So the big takeaway here is that the industry's solution to context limits, just building bigger and bigger context windows like 1 million or 10 million tokens, is like just building houses with bigger and bigger desks instead of inventing filing cabinets and libraries.
It works, but it doesn't scale. This paper argues we don't just need a bigger desk, we need a whole memory management system. We need the filing cabinets, the libraries, and the smart librarian to run it all.
And it turns out the blueprints for how to build that system have been sitting there waiting for us since 1961. It's a brilliant application of an old idea to solve one of the biggest problems in modern AI.